Hello, good morning, everybody. I'm glad to see such a big turnout here. You know, that's shame what's happened with the exhibit hall, but you know, I'm sure that you'll be able to get an awful lot out of the keynotes that we have here. We're going to see a keynote here now from Mellanox and eBay. You know, delighted to have somebody from eBay here. That's how to network flash storage efficiently at Hyperscale. The speakers, there are actually two speakers, one from Mellanox and one from eBay. Michael Kagan is going to be the speaker from Mellanox. He is a co-founder and CTO of the company, where he focuses on improving system performance through high-speed networking. He works on problems in high-performance computing, cloud computing, and mega websites. He has led efforts to establish new standards in high-speed networking with particular emphasis on RDMA and converged Ethernet and the InfiniBand technology. Before joining Mellanox, Mr. Kagan worked at Intel, where he managed the Pentium MMX design and the processor's architecture group. He holds a BSEE from Technion, the Israel Institute of Technology. And I am told that he likes to take Mellanox Israel visitors on hair-raising four-wheel drive rides into the desert. So there's a wild side to this man. Our other speaker from eBay is Manoj Wadekar. And Manoj is responsible for eBay's data center hardware architecture after having held architecture and design positions at QLogic and Intel. This hardware supports the e-commerce for thousands of online customers. He holds a Master of Technology and EE degree from the Indian Institute of Technology in Kanpur, India. And something interesting about him is that he has brought part of his mother country with him. Manoj helps to bring Indian culture into the Bay Area through his participation in the managing committee of the California Arts Association. It's a nonprofit theater group that he says that they built and have been running for the past 15 years to keep the culture alive for his family and that of others in the area. He also told me that he sometimes wishes that he was related to a very famous Indian cricket captain, Ajit Wadekar, although sometimes he does pretend to be related to him, especially when India's team is winning. So that's the other side of our speakers. Anyway, I would like Manoj to come up and speak. Here we go.
Thank you, Jim. Good morning, everybody. I would like to say that this event has been growing a lot. I've been coming to Flash Memory Summit for a long time, and this has really grown a lot, and I'm really happy to see all of you. And let me talk about eBay's infrastructure and what we are doing from the server point of view as well as from the storage point of view and how it is growing. So eBay has been growing in the marketplace, as you can see, significantly, although the first slide is missing. Let me talk about that. That eBay's growth has been driven by the listings and the sailings in the data center, and that growth is really supported by our infrastructure, which has been growing in capacity as well as performance. As we continue to grow for that, we look at various trends that are happening in the server as well as server from compute point of view, memory, and storage. When eBay started back in 1995, the storage was dominated by a hard disk, and the network was 1 gigabit per Ethernet, 1 gigabit per second. And it has the scale-out storage that eBay's applications required was really driven by converged infrastructure where the compute and storage were tied together. Now, as we see the storage density is growing significantly, as we saw some of the announcements yesterday and some in the industry, as well as the performance that is being driven by NVMe and other technologies. Question is basically now this infrastructure, is it the right infrastructure to continue? Is it perhaps the time for us to look at it together? And that's what we'll try to do in the remaining infrastructure, in the remaining presentation. So you can see that eBay's hyperscale infrastructure is typical of many of the hyperscale infrastructure out there, where you will see search, Hadoop, database, front-end DevOps, and object storage, and machine learning and artificial intelligence. These are the kind of high-level examples of server clusters that the eBay infrastructure needs to support. This has been growing consistently over many years to keep up with the capacity as well as performance needs that eBay's listings and sailing demand continues to grow year over year. So the footprint has been growing. For example, Hadoop footprint, which started back in single-digit petabytes, now has grown over multiple hundreds of petabytes and continues to grow year over year very aggressively. The search clusters have been increasing as the listings continue to grow, as the sailings continue to grow. Similarly, DevOps as well as front-end workloads, databases have been continuing to grow consistently. So the scale of the infrastructure is not obviously counted in the number of servers anymore. It's done in the rack level. So rather than being measured there, we are continuing to look at how do we do efficiently the whole rack deployment in the data center. So when we drive the performance and capacity need of the infrastructure, we have to keep in mind that this is getting multiplied by very large numbers. So the efficiency is extremely important for that. So the goal is to drive the high performance that our infrastructure needs to provide to keep eBay running at a speed that we expect at a performance and continue to grow at the capacity that we need. It is absolutely important to make sure that infrastructure is designed with efficiency in mind and there is less wastage of the resources. Now, if you look at that, then how do we really design our servers? So what are the typical hyperscale servers? So we are defining them at a rack level. So the racks are comprised of the same type of servers being loaded into the rack. They get what you call as a rack and roll. That means the whole rack comes to the data center, gets plugged into the power and network, and we are ready to use it for the applications. Each server is going to be defined by the need of the application. What's the compute need, what's the memory need, and more importantly, what's the storage need. Now storage, let's focus a little bit more on the storage. We looked at various applications in the previous slide. What are the storage requirements that gets defined into these servers? So as you can see, if you look at memory, the memory tends to be where the data gets stored if you look at the search, so they are more in-memory databases. And then it continues to go from that to the databases, to the Hadoop, to object store, front-end DevOps applications, and goes to the archival, to cold storage. So you go from memory to cold storage, which may be dominated by hard disk or tapes and equivalent storage devices based on the performance and capacity needs. And of course, the need for how much you need is also changing as you go from the top to the bottom. Flash has started really growing significantly. It started at a level of databases and similar applications in the beginning in the top tier. And it started going, it's going to go to the top using the SCM kind of technology, but also it is getting into the middle tier as we see the density increasing for the flash, but as well as the business aspect are basically improving also with the cost perspective. So flash is growing significantly. But the question is basically, as we design this into the server footprint on a single server, question is, can I really take advantage of this high performance and high density storage in each node, or is it going to be relegated only to certain applications which are very small in the number and really demand that density as well as performance? And this is what will bring us to how do we define the server in efficient way where we can take advantage of this technology that are growing. We saw the technology announcements in last 2 days about very, very high densities in storage, very, very high performance flash. Question is basically, can we use it? So coming back here, this is how the infrastructure for eBay or any hyperscale is going to be always going to trade off between what's my capacity and performance goal and what's my efficiency that I can achieve and maintain the year over year growth of the performance as well as capacity, but make sure that we are optimizing the total cost of ownership for the data center. So now this brings us to what's our current design. So current design, if you remember, we talked about the scale-out applications have been designed with a converged server definition where it's going to be compute and storage are co-located, and that's what you drive the economies of scale by maintaining small number of server SKUs. You want multiple applications. We talked about in the previously. We want to make sure that we can maintain those small numbers. That way we can have large number of servers being deployed at much higher economies of scale. What it means is multiple applications are going to start sharing that particular server. And that potentially leads to some inefficiency. Because there is a discrepancy. When applications start sharing, it's very difficult to find exact match of what their utilization is. And the schedules are very complicated. So what happens is that you have, let's take an example, you have a front-end app and a database app sharing the same server. You'll say very likely is that database is going to require maybe perhaps good amount of memory and a very high amount of storage, perhaps lower amount of compute as compared to some other application. But if you think of front-end apps, you will see that if you're going to deploy it on a VM, you are going to occupy a certain amount of memory. You're going to use a certain amount of compute based on the application that is run on that. However, very little storage. So you'll see there'll be significant wastage that can happen with such kind of deployment. Take an example of Hadoop. You'll see MapReduce and Spark will have different usage model for their storage and compute and memory ratios. So creating that single SKU for the application can potentially lead to a significant inefficiency that gets translated to very high number and becomes overall TCO very, very challenging. This is something that we see after 20 years of what we have been deploying as a hyperscale. Now, the other solution could be, well, why don't you just split the SKUs? Get the SKU for application which is running front end and get one SKU for database. What it leads is basically multiple SKUs drives down your efficiency because you're creating large tax on the overall space, power, and cost in the data center as we start deploying multiple SKUs. That siloed infrastructure is definitely not something that helps the overall TCO. And the other challenge that we talked about was how do I really use new technologies? So this is the further challenge when we have compute and storage tied together in a single server. Because how much performance you can use and how much density you can use of that storage in that given node is defined on how much compute and memory I put in that and what application is going to use that. So I have a choice between either creating a very cost efficient but underperforming SKU, which means, for example, I may have lower performance storage and maybe lower density storage for that matter, or I can have really high performance, high capacity, but it's not going to be very cost efficient. And this is the challenge as we saw that pyramid where the flash, how does it really take advantage of the higher density and higher performance is typically tied to this converged server design. The last challenge happens, which is not necessarily exactly related to the converged, but the way the deployment has been happening, which is if I have a deployment where I have a cattle type of scheduler, we're going to say if a container dies, it dies, or VM dies, it comes up somewhere else, and you start the life where you are from. It's like a stateless app. That's not true for the storage-heavy applications, because they're going to store a lot of data locally. If a container dies and comes somewhere else, or same with a VM, that data needs to move. That data needs to get replicated. So more storage you put on a given node, there is a high probability that you're going to move that data, or you're going to make a decision between how long you can survive with the durability challenge, high availability challenge from data perspective, and then postpone the problem of replicating the data. So this is what actually happens because we tie compute and storage together, and at this point it looks like we are shackling the storage to the compute, and the growth of or utilization of higher performance and higher capacity, higher performance storage is going to be tied because of how that server SKU is going to be defined. So where do we go from here is that this is now the question we look at and saying that is this a time for the swinging pendulum again? Is there a way now we look at what's our compute, what's our storage, and most importantly, what are the network capabilities? Can I get more flexibility by now separating out the compute and storage and scale them independently? Can I disaggregate the storage? Can I create a definition which will allow me to use that high performance and high capacity storage without giving up the flexibility that I have today to deploy the applications more flexibly? And this is where we look at how are we going to use that, what kind of network we are going to do. There are multiple networks that can allow us to do this, where we have CPU, which is the node which is more CPU and memory bound, and then a storage server, which is basically providing the storage capability, connect it over the network and create more fluid and flexible SKUs. The networks could be multiple. There are multiple ways people have been tackling this question. It could be PCI, it could be SAS, it could be InfiniBand, it could be Ethernet, multiple of those. We do think, and I'll talk about why we think Ethernet is a really good way to go about it, but there are multiple options that people can use to solve the fundamental problem for how do we disaggregate. Let me tie it back to how we acquire and utilize. Again, coming back to the rack. As I said, the scale of our infrastructure has grown so much that we really do not look at servers as those one nodes. When we consume, we are going to look at them as racks of servers. We're going to look at how many cores I have, how much of terabytes of memory that rack contains, and how much of petabyte of storage that rack going to contain. So if that is the case, what disaggregation allows us to do is look at the storage differently. Instead of looking at a node local storage and have my scheduler constrained to say that I need to land it in that particular node, we can make it more flexible and we can make it at a rack level. If a rack is comprised of a compute-heavy servers and storage-heavy servers connected over the network, I can look at the same footprint of storage capacity and compute, but give more flexibility, who uses what, and not really land that storage particular to that node and not allow other nodes to use that. Make it more flexible, make it more efficient, without really giving the performance needs that particular application demands. So this will allow us now to say, for example, if I'm running front-end and database app, I know how much I can use for database and have that much of a storage capacity in that rack. And front-end applications, if they are running, they really don't need to use that storage capacity. They could be used by some other nodes which are going to be running the higher storage demand or higher performance kind of application. Makes the schedulers much more simpler. Now, this is of course a journey to go from where we are right now, but this is a consideration right now that start looking at rack as a compute and see how we can deploy the storage in that constraint, and that allow us to really be more efficient, more flexible, and allow to use the newer technologies. What it would do is basically, as I said, this will allow us to do right sizing. So if I was going to buy hundreds of racks which are going to share front end and database, I can start looking at saying that instead of wasting the storage on the front end servers that were running, or the servers on which part of it was running front end as was wasting the storage capacity, we can start resizing the racks and make sure that it rack has the capacity for whatever number of database VMs or database containers we are going to run. So allow the wastage. At the same time, I can now start using more performance storage there. Here's another way of looking at it. If I had a storage, very, very high performance storage on a particular compute node, that is going to be used by only those nodes, those cores. So if you had a 2-socket 16-core CPU there, you're going to get 32 cores to drive that performance. But imagine if that storage was going to be used outside. I can use aggregate bandwidth, aggregate IOPS, and overall capacity of that storage being shared by multiple nodes, and now I can start driving higher performance storage much more efficiently in data center. So that also brings up another point of how we really can start designing our racks. Today, since the compute and storage are bound together, they really go along together. So I'm going to get in new storage typically when I have a cycle coming up for my CPU refresh. CPU and storage don't necessarily evolve at the same rate. If you look at for last 4 years, cores have perhaps doubled. Storage had quadrupled last year, I checked, but now it has done much more than that if I look at flash densities that are going up so dramatically. So the densities as well as performance and capacities for core and storage, they don't go necessarily hand in hand. Separating them from each other will allow us to get that kind of independence of scaling and independence of refresh. So coming back here now, what really does it mean from the network? So we said, okay, we can take what storage was sitting inside the server and move it out. Now, of course, that it means that there are expectations from that server. We said we're going to have multiple nodes that are going to be sharing that storage, because I had a 6 terabyte sitting inside one node and then moved it out. And I got now suddenly 60 terabytes sitting into one storage server, for example, is going to be shared by 10 servers. That means I need high throughput. I need high IOPS that particular server needs to drive. I need to have a latency that the application demands. We are sitting on the PCI or SATA or SAS bus locally to the compute. The moment you go across the hop, can you keep up with that? Can you provide that kind of throughput? Can you provide that latency and consistency of latency? Database applications demand 95th percentile latency to be consistent. So can the internet, can the Ethernet can keep up with that? And most importantly, I said Ethernet because that is a strong requirement in our data center because of it, the ubiquity of Ethernet, because of the simplicity and overall way it fits into our infrastructure and makes it available for everything. So Ethernet would be the right choice for this disaggregation of the storage. Question is, we started from 1 gigabits per second Ethernet some time back. Now where are we? Is Ethernet ready? Can we take this big step and make the data center easy? Let me call Michael on stage and ask him that same question. Thank you.
Thank you. Good morning, everyone. If I would read the introduction script, I would probably use some four-wheeler to get on the stage. But so that's for next time. Now, so the question was whether Ethernet is ready. And the answer is yes. And now I need to figure out what to do with the rest of 15 minutes that I got here. So we'll talk about why it's ready. So we are in the world of shifting the paradigm. Everything becomes a service. We don't talk about computers anymore. We talk about computing. We don't talk about disks anymore or storage servers anymore. We talk about storage as a server. And each application requires a data center running serving millions of users, running millions of applications. And each application requires a different type of services, and the ratio between these services are different per application. So it means that when we run this stuff on the data center, we need some sort of dynamically assign different services to different applications. And the way it's done is you segregate the server as a physical function versus service that you provide, and it's called virtualization. So application that runs on top of virtualization layer can use hardware resources all over in the data center over the network, and it is pretty much transparent to the application. So in order to make it work efficiently, you need to be able to allow application to operate the resources on the different machines. And RDMA is the remote direct memory access, is the key technology, underlying technology that enables this type of operation. So you can access the resource, memory, or actually any other resource on the remote node directly from the application that's running on the client machine. And the way it's working, it is not only fast in terms of latency and bandwidth, but it also doesn't require any resources or very minimal amount of resources on the target machine for the application to use the services. So RDMA was introduced on Ethernet about a decade ago, Oroki, RDMA over Converged Ethernet. And this is what enables to access segregate the resources. So RDMA enables to implement virtualization layer at relatively low cost, very cost efficient. So it actually, the virtualization layer itself is not using computing or using very minimal amount of computing, leaving all the compute power in the data center for the application. Now, getting back to the storage, and Manoj talked about storage a lot, the network technologies have been used for quite a while for storage virtualization. It is decades out there. And legacy networking, or today's the networking, was good enough to virtualize storage because media performance were relatively slow. And therefore, the storage protocol and the network access to the remote storage was really negligible comparing to the media access itself. So storage is network storage for a while, but things are changing. With introduction of flash devices, the media access improved by 2 orders of magnitude. And now the overhead of software protocols and the traditional networks becomes noticeable. Now, looking at the not very distant future, and there has been multiple announcements about this yesterday, with the introduction of yet another tier of storage technology, which is non-volatile DIMMs, the performance of media or media access will be improved by yet another 2 orders of magnitude, which means that the traditional network protocols and traditional networks and the way the storage was accessed over a network, it becomes inadequate for this type of speeds. So NVMe, NVM Express, was introduced to reduce or actually to cut down the overhead of the software SCSI protocol on the for the local media access. And if you take the same media and put it on the SCSI interface versus on the PCI Express interface, you can get almost all order of magnitude higher speed of storage access on the local node. Now, storage without network is not very meaningful, and we talked about the virtualization and the ability to assign resources. So now, with the NVMe semantics that were introduced to accelerate the storage access on the local node, this semantics needs to be extended over the network. And that's what NVMe over Fabrics is all about. It was introduced, actually specification was, the first revision specification was released about a year ago, and it relies on the RDMA-enabled fabric. So all the data transfers and actually all the protocols runs on top of RDMA. So NVMe over Fabrics, this is what enables to extend the efficient access to the media, NVMe media over the network. And this is industry standard today. So NVMe over Fabrics, but what is the fabric? So there's a question, what is the fabric? The answer is Ethernet, and the fundamental reason why it's Ethernet, because Ethernet is that's what is used in the data centers. Ethernet is a ubiquitous fabric that is being used everywhere, and it moves forward in terms of speeds and feeds, and it also moves forward in terms of enabling different storage protocols on top of Ethernet. We talked about the RDMA. NVMe over Fabrics runs on top of RDMA. Ethernet today is in the production for 100 gig speeds, and it is on the verge of introduction of 400 gigabit Ethernet. And being fabric of choice of the data centers, and with the volume and the inertia, Ethernet becomes the fabric of the data center. So performance, efficiency, and ubiquity, quality of service, security, everything that traditional storage area networks have been doing, now it's available on Ethernet. And, all the protocols are being ported to Ethernet, and Ethernet can actually be will be the storage fabric of the 21st century. So NVMe over Fabrics, the efficiency of NVMe over Fabrics is actually tremendous. You you're able to access the remote media, remote storage at the same performance or very similar performance versus local media. On the cost of a few microseconds additional latency, you get pretty much the same bandwidth and the same I/O operations over the remote access, accessing the remote storage versus local storage. And this what actually enables to segregate the storage media and the storage computing that Manoj was talking about 10 minutes ago. So now you can build a NVMe JBOF that exposes NVMe devices to the clients on the network via RDMA, and it doesn't require any significant processing power, because RDMA doesn't require any processing power. So Mellanox introduced Bluefield product family. It is integrating the best breed of our network adapters and industry standard ARM cores. The Bluefield integrates A72 ARM cores, and this is a product family that will have multiple members and multiple products out of this product family, from device or boards that will enable to build JBOF, to build I/O controllers, so you can, at very low cost, connect multiple NVMe devices and access them, present them to the network for client access, so you can have an NVMe or Fabric server. And you also can have a Bluefield family member product as a standard adapter that can be used on the host, and it can provide additional flexibility through the ARM cores. And one of these flexibilities is actually being able to serve the accesses to the local NVMe devices from the remote machine without any interference with the local CPU. So you can completely segregate the computing and the storage tiers in the hyperconverged data center. So Bluefield has two ports of 200 gigabit, of 100 gigabit per second. So it will deliver total bandwidth. Actually, we can demonstrate delivering total bandwidth of 200 gigabit per second from a single JBOF. So looking forward, there is storage class memory is around the corner, and this is yet another tier of storage or memory or storage class memory. And there is additional semantics developed to access and to operate with the storage class memory. So when storage class memory hits the market, we will need to extend the semantics over the network pretty much similar way as NVMe over Fabric extends the NVMe semantics over the network. The storage class memory semantics will need to be extended as well, and industry works on defining, we are actually in fairly advanced stages in the IBTA defining how to extend storage class memory semantics over the network. So just looking backwards and looking forwards, network technology was advancing at speeds and feeds following Moore's law. It's a great law of exponent. Mellanox was introducing a new generation of technology, doubling the speed of the network every 2-3 years since we started the company. But not only doubling the speed, we also added more and more and more capabilities to enable additional services to be delivered and to build the data center in a much more efficient way. The vision is that we need to enable to build the data center scale computer that will enable to deliver more services that are not cannot be delivered with the traditional networks. So more capabilities, more performance, more protocols, and more industry-wide initiatives. That's what we are about. And now, if you have any questions or remarks.
I'm afraid that there really isn't time for questions now. But anyway, I would like to have a great hand for Michael and Manoj. Thank you very much.